I'm going to talk about buildings. So you guys have spent the whole quarter learning about energy and how energy is produced and all these different things. I'm going to talk more about how energy is used. So what we call the demand side of energy. There's the supply side and the demand side. Okay. So buildings are a big part of the demand side of energy. A little bit about me. I've been working in buildings pretty much my whole career, and I've founded now 3 consulting firms. The first 2 I sold and are successful parts of bigger companies now. I recently founded a consulting firm, smaller one, called Decarbonization Strategy. So I focus on building decarbonization. I also founded a company called Personal Comfort Systems, which was not successful, but I love the idea. It was we were making a heated and cooled seat for office environments, which I think is like an idea before its time. But the number one complaint of people who work in buildings is I'm too hot, I'm too cold, especially commercial buildings like offices. So anyway, and I published the first article on building decarbonization in FASHRAE Journal, which is the Journal of Heating and Cooling Systems. It's a US-based organization, but with international membership. And you're going to see why I published that article in a building about heating and cooling systems, because heating is a big nut to crack as far as decarbonization is concerned. Okay, so Diana loves me to tell this story, which is, I was a young engineer. I went to school at Berkeley, by the way. Don't hold it against me. But I have a lot of love for Stanford. But I was working at the Solar Cal Council hotline, and before the internet, you would call a phone number to get information. The 800 number was like a big way of getting information, or you could go to the library, So we would take calls on solar systems for buildings, and I got a call by somebody saying, "Hey, I'm looking for a solar clothes dryer." And so I was a young engineer. It was an internship. I was in college. I started thinking mechanical engineer. So I started thinking about like big ducts and fans and a big system that sort of looks like this, And then I said to the person, "I'm going to put you on hold." And I said to the other folks in the team, like, "Does anybody know like what a solar clothes dryer looks like? Because I have a call about that." And they all started laughing. And I was like, "What?" They said, "Peter, you just got pranked." And I'm like, "What do you mean?" So they said, "Well, your solar clothes dryer is that, just a clothesline outside in the sun." And so I was like, "Oh, okay." But that that was actually a really important lesson, and one that it's been echoed in many other things when I've really gotten into the details of buildings, is that we can design buildings that are really complicated and have lots of moving parts, but are not necessarily reliable, and at the end of the day efficient. So that oftentimes a simple solution works best because it's reliable and it's something that we can count on, as opposed to really complex things. So why are battery electric cars popular? We were just talking about that. There's a lot of different reasons, but one of the big reasons is that they have significantly fewer moving parts in electric cars compared to an internal combustion engine, where there's lots of parts in an engine. And I think it's several thousand fewer parts. And so the battery electric car has significantly lower maintenance. It's just simpler. So anyway, lesson learned. I try to follow that philosophy. Basically, what I've been doing in my career is trying to hack building systems and buildings and how buildings work. I'm an engineer that works on building design. So I think about the heating and cooling systems, electrical systems, plumbing, energy, water, all those things, how the building works and how it's going to perform. So the way building industry works is this is the way we do it. This is what when I was younger, the older folks would tell me, hey, this is the way we do it. Don't rock the boat. It works. We're making money, and we're good to go with this. So really what needs to happen is disruption. And there's been actually a lot of disruption in how we think about buildings and how we design them over the last few decades. And it's a really exciting time to work in buildings. So I've been fortunate to work in a lot of very high profile buildings and lots of LEED platinum buildings, which is highest level, and then also as an early innovator in what we call net zero buildings, net zero energy, net zero carbon. So that's sort of where we're going. So I'm going to talk about buildings, but also from this perspective of what is a decarbonized building and how it works. Okay, so what are the climate impacts of buildings? Anybody know what is how many tons of CO2 equivalent per year are emitted globally? Anybody know roughly what the number is? 53 billion tons per year. So it's also known as gigatons. It's a little bit disappointing. I'm sorry. I don't want to bring you down, but bad news first. Start with the bad news. It's a lot. But the interesting thing about that, and that's globally, okay? The interesting thing about that, okay, think about 53 plus or minus. 2.4 billion tons of CO2 are from fossil gas used for heating in buildings. So, whoa, that's a lot actually. And when we say heating, that's 68% space heating, 19% water heating, so it's mostly space heating, then some water heating, and then some other miscellaneous things, including cooking. So if we add that up, if you include not just fossil gas, you include electricity. So there's a lot of heating with electricity. It comes up to 4 gigatons of CO2 emissions. So that is roughly about 8% of all global greenhouse gas emissions are relating to heating in buildings. Okay, so Arun Majumdar, who's the dean of the School of Sustainability here at Stanford, he likes to say, I want to talk about solutions that relate to a gigaton scale. Don't come to me with the little things. I want the big things. And so heating is actually a big thing, and we're going to talk a little bit about that. But if you look at this graph, the 27% of all carbon emissions are relating to building energy consumption. And if we include the emissions relating to manufacturing building materials, biggest part of it is concrete, cement, and then concrete, but also steel, glass, all these other things that we need to build buildings. It comes to close to 40%. Some numbers are 35%, 40, somewhere in that range of global greenhouse emissions relate to buildings. So buildings on the demand side are a gigantic part of the problem. And also I like to think a huge part of the opportunity, right? So the other thing you guys have probably learned about this, but greenhouse gas or burning fossil fuels does create air pollution that directly impacts people's health, right? So worldwide, it's about 1 in 5 deaths is related to pollution from fossil fuels. Right. In the US, that's 350,000 deaths per year. So this is a huge thing. There is debate about, and not my mind, but people like to debate, climate change and all these other things, but there is this like direct thing that's happening right now, not necessarily in the future. So that's happening. And then in the US, Black communities do bear a disproportionate burden of the use of fossil fuels for a variety of reasons, but there's also an environmental justice part of fossil fuel use. So for all those reasons, I think that building decarbonization should be a main focus of when we're talking about how do buildings work. I'm going to cover how do buildings work roughly, but I'm also, this is the energy class, going to talk about building decarbonization and how that works. So what we say is the part of the carbon emissions that relate to construction are called embodied carbon. And then the part of the carbon emissions that relate to energy consumption is called operational carbon emissions. Okay. And generally speaking, operational carbon emissions, if we look at it either at the national level or international level, the operational carbon emission is bigger than the embodied carbon, but they're both significant. So let's just dive a little bit into the embodied decarbonization concept. So if you look at what are the ways of dealing with that? When we look at buildings, the largest part of the embodied carbon is the structural system. So that is, how do we hold up the building? What's at the core of how the building is held up and built? And that is, generally speaking, in commercial buildings, steel or concrete. And in residential buildings, it can also be steel, concrete, but also wood has a bigger role to play globally. Again, depends on where you are. In the US, a lot of residential buildings are already made with wood. I live in a house that has wood studs, right? But then there's other things like glass and furniture and a variety of other things, but over 50% of the embodied carbon in buildings from the structural systems. So right now there is a lot of discussion about alternative structural systems. We can move from concrete to steel, and a lot of markets are in commercial buildings. A lot of markets have already sort of moved there. It depends on a variety of cost things, but we can also now start considering wood structures as a type of structure. And one of the areas of research here at Stanford is there's a lot of research on the embodied carbon of cement, because globally cement is responsible for somewhere around 5 or 6% of greenhouse gas emissions. Just cement alone is huge. So can we manufacture cement in a way that has much less greenhouse gas emissions? There's a lot of research on that going on here. But what most people are doing to decarbonize the embodied carbon of a building is they're looking at low carbon building materials, primarily the structural system. And then even wood does have an embodied carbon associated with it. If nothing else, transporting it, cutting it and getting it ready for building materials does have a carbon emission related to that. So it's not possible right now to get to zero. So what a lot of folks are doing is they'll do the best they can, and then they'll use a carbon offset of one sort or another. So carbon offsets are a way of avoiding carbon in somewhere else so that your project's carbon emissions are offset. So you guys, I assume have talked about that. So if we look at some of the numbers, this is for a 175,000 square foot office building that I worked on. We looked at using what was the difference between concrete, steel, and wood. And you can see it went from about 30 million pounds of embodied carbon down into, the low 20s. So that's a good, if we use steel, but if we went into wood, we're cutting it almost in half. So there's still emissions related to wood, but and so there's a lot of buildings now being built, not high rises, but remember, most buildings in the world, commercial buildings, are low rise, anywhere from 1 story to 5 to 10 stories. That's the vast majority of square footage. So Google, for example, just built a very high profile building with mass timber, with timber as a structural system. And they're talking about it a lot, and they're looking at their future buildings using timber as a structural system. So that's happening. And then one of the companies that's making a lot of progress on low embodied carbon cement. Is called Carbon Cure. And what they're doing is injecting captured CO2 into the cement. So that's like a sort of a creative way or interesting idea. We'll see how far that gets, but that's an interesting thing. And there's a lot of additives that can be put in the concrete mix that makes it still strong, but is taking sometimes a waste product or organic product and putting that into the cement instead of having to put in more cement, which is high embodied carbon. So there's a lot of things that are going on. I'd say that field of embodied carbon is still evolving, and we're in the early days, but operational decarbonization is actually quite evolved. Yeah.
How long will wood last if used to build the structure of a building?
So if the building does not burn down, okay, which is the thing, if a building burns, it actually emits all that CO2 into the atmosphere, right? And we can say wood is a sequestration of carbon, so it's actually pretty good if you put it all together. But wood structures that are properly rainproof, which is like a good roof and things like that, can last, 100 plus years. And so most buildings that we're designing that are environmentally trying to be sensitive and thinking about these things, if we can design to 100 years, we're in pretty good shape. And if we can possibly reuse some of that. There are buildings in Europe that I've been in that many have stone, okay, which is pretty low embodied carbon, just a stone, not concrete. But there's buildings with, wood, rafters and things like that that are, a couple hundred years old. Yeah.
Are there any conversations going on about deforestation when using wood for buildings? If so, what are some measures being taken to avoid deforestation?
This gets into sort of a deep thing about like environmental trade-offs, but generally speaking, the wood that's used in buildings is farmed wood. It's not wood from virgin forests, and it is considered to be, capturing carbon from the atmosphere, putting that into the wood that then goes into the building that hopefully lasts a long time. So there's that, but there is land that's taken for growing wood, and obviously a virgin forest with old growth trees would be good, or is a better environmental thing in that location. But from an overall carbon perspective, using wood instead of cement, it's better. Yeah. So yeah, that's a very difficult subject, the carbon and the environmental trade-offs when you start to look at everything. And one of my mentors said, Peter, there's no free ride. Even solar energy has an environmental impact, right? So we're just trying to get it to be really low. Okay, so let's get into this idea of operational decarbonization. It's pretty straightforward, actually, how to get to operationally decarbonize buildings. First, we need to make the building efficient, energy efficient. I'm going to talk about that. And then we have to make an all-electric building. And then we connect that efficient all-electric building to renewably generated electricity. Right? And you guys have heard about solar and wind and all these things that are doing pretty well right now on the grid level. So if we connect that efficient all-electric building to renewable electricity, that's how we get to zero carbon emissions, or as close as humanly possible, right? So let's talk a little bit about the efficient building. Energy efficiency is really big. So if you think about lighting in buildings, when I was a kid, the only light that was available to buy for your house was an incandescent light bulb. Okay, now when I go to places like Home Depot or the local hardware store, it's hard to get anything but an LED light bulb, light emitting diode. In the middle, between incandescents and LED light bulbs, were these compact fluorescent light bulbs that you can see in this classroom. This classroom was built about 10 years ago, 15 years ago. So LEDs were not that easily available, and they were still like, is it good enough for us yet? So this has compact fluorescence, which if we were building this building today, we'd have all LEDs. So that's a huge thing. So if you look at like LEDs, the energy consumption goes from 60 watts to 11 watts. Now you can actually get that same 60 watt bulb in 8 watts LED. And LED light bulbs last almost 10 times longer as compared to incandescent light bulbs. So significantly better. Now, when LED light bulbs came out, I remember they were really expensive and they weren't very good. They were like $10 to $15 for one. And an incandescent light bulb was like 50 cents or $1. And that's just buying it. But then the energy consumption, if you add it up over, the lifetime that you're buying all these bulbs that are burning out as compared to LED, and it's going to save the cost of a light bulb several times over. But now the LED light bulb costs around $1. So it went from $10 to $15 to down to $1 in about a 15, 20-year period. So a lot of these things, when they start expensive and then over time get cheaper. So you're going to see that pattern. Another thing that we've done in buildings to think about energy use is daylight. And daylight, we're now designing buildings to take advantage of daylight. Can you design the building that brings light in, but without all the glare and too much light? It's not just a glassy building, but it's a building where daylight was thought of carefully, and we can use daylight to light spaces. So what they found is that people perform better in spaces with daylight. They've done studies on schools and found that school class or test scores for children in K through 12 schools are better, significantly, measurably better in classrooms with daylight. Interesting. And the large retailers in the US, Walmart, Bass Pro, Stop and Shop, these big guys have done their own tests. Walmart did one where they had a big superstore. They had half with daylighting, simple daylighting, skylights, but well placed, thoughtfully done. And then the other half with just electric lights. And they put the same product on each side. They would move it from one side to the other. And what they were finding is that the sales were up to 40% higher in the area that had daylight. The products were doing better in the daylit part of the store. So, and Walmart figured this out about 15 or 20 years ago. Now every single store that Walmart builds has skylights that are thoughtfully placed to create daylight. Daylight is a better version of light because it has a full spectrum. It's something that our eyes evolved under. It makes us feel more comfortable and our eyes relax more, the whole thing. So daylight is a really big deal. And lighting. When we start looking at plug loads in buildings, plug loads are actually a really big deal. If you think about buildings, we've got the lighting systems, we've got a heating cooling system, but all the stuff that we plug in is a very big energy user. So in this classroom, these projectors, if you're plugging in a laptop, if there's something like a copier or a coffee machine, all those things that get plugged in are what we refer to as plug loads. So when we first started using computers widely in office buildings, they used typically around 150 watts or more. There was a computer and a screen, and the screen wasn't the thin LCD screen, it was a deep cathode ray tube screen. This was not very long ago. That setup used about 150 watts. And then we've now moved over to laptops with LCD screens, and together, similar size screen and the laptop can use about 35 watts. The power consumption of computing equipment has dropped dramatically. And now when you have a laptop, desktop, or laptop or pad, whatever, those guys use somewhere in the neighborhood of 5 watts, sometimes 10 watts. Very, very low energy. And the energy's been brought down in large part so that the battery life is extended. So anyway, that's amazing what's going on. Now we have a lot more computers today than we used to, right? It was sort of a like a special thing to have a computer. Now it's a requirement that absolutely everybody in an office building has a computer. And now we carry around a cell phone, which is in a sense a computer, right? So um, now we start thinking about heating and cooling in buildings. Let's again, staying with the large building concept. We started with these systems called constant volume systems, and we moved to a variable volume system. It's sort of like changing from a car that's always running at full speed and you control its speed by, putting the gas or the brake on. That's how it used to be in heating and cooling systems. Now they vary the volume up and down based on the need, right? So varying, that's saved a ton of energy and it's an evolution. And I remember when I was young engineer working on buildings and I was asked by my boss, like, figure out what is this new thing called variable air volume. And so I called a few engineers around, older guys, and they were like, oh, that variable volume, it's like, it's too expensive. It doesn't work. It's like a ridiculous idea, blah, blah, blah. That's what I was hearing. And fast forward to where we are today, like nobody uses the constant volume system and everybody uses the variable volume system, including in this building, right? So that's been a huge energy savings. So a lot of these things have evolved as we've started to think about, wow, energy does actually cost money and makes a difference. But there's so many more things that we can do. When they start thinking about pumping systems, this is what I designed pumping systems and fan systems. You can track that to how many watts are required for each gallon per minute of water that you're pumping to heat or cool a building, for example. And the way a standard building goes, it's usually about 15 watts for every GPM, gallons per minute. When I really focus in and do what I consider to be a really good job, I'll design a low friction system that has smooth pipes and thoughtfully designed. I can get it down to 7 watts per GPM. But if we compare to the human circulatory system, and you can look these numbers up, it's close to 1.5 watts per GPM. So we're still in buildings nowhere near as good as the human body, which is amazing. And each of our bodies has 60,000 miles of blood vessels, just to remind you how incredible the body is. So not only amazing with 60,000 miles, but it's also super energy efficient. Anyway, so I like that. So there's a lot of blockbusters that have already become standard in buildings. LED lighting is one of them. On the top right is the variable air volume. That's the box that varies the volume. It has a damper in there and such. That's been huge. Then the lower left is low E glazing, low emissivity glazing, which this building has and most modern buildings have, and just even in residential new homes, it's widely used. And what it does is there's a thin film that you can see through, but blocks the infrared part of the light. So if you're in a hot climate, it will block the heat from coming into the building. If you're in a cold climate, it will keep the heat inside the building so it doesn't leak out. Not 100%, but it really slows it down. So it's a big deal. And then the bottom right is a box that has a variable speed drive that controls motors to ramp up and slow down. So think all the fans and all the pumps that we have in buildings. And then if there's a compressor for air conditioning, we can speed those up, slow them down as the need requires. And that is gigantic. All of these things have been huge. They say on LED lighting globally, it's reduced the need for a few hundred power plants are no longer needed because we have more efficient lighting as compared to the incandescent lighting. So big deal. If we look at when we started focusing on energy efficiency in buildings, it was really during the 1970s when we had the Arab oil embargo and the oil crisis. So that was something that brought energy into focus globally. And so one of the things that happened is that FASHRAE, remember that organization deals with heating and cooling, together with Illuminating Engineering Society, which is the lighting guys, got together and said, let's think about creating an energy standard for buildings. Like, what does an energy efficient building look like? So we created the standard that in the it was 1975 when it was first created. If we compare a building that was built in 1975, where that standard was saying this is a more efficient building, to where that's just the standard is, which is not very hard to meet with today's technology. The new version of it, it's a 50% reduction in energy. So that standard, which is considered to be pretty easy to meet, has resulted in a 50% reduction in the energy use of new buildings. So that's kind of amazing, because I ask a lot of people, how much energy do you think we can save in a building? It's like, oh, 5%, 10% maybe, but it's already been 50%. And if you look at this graph that I did recently for a project in North Carolina, I was working with the electric utility there called Duke Power. We took that standard, the FASHRAE 90.1, the energy standard, and said, okay, let's put that as our starting point, the bar on the far left, and let's apply things that we know how to do today, new things, a better building envelope, better lighting, addressing the plug loads, the low friction system, right? And heat pumps, which I'll talk about. We can just very comfortably get another, in this case it was 44%, but let's just call it, we can comfortably and easily get another 50% energy reduction. So that's also significant. If we start adding in photovoltaics on the roof of a building, a modest amount, we can get to 70%, or in this case, we're modeling, I think it was a 3-story building. We cover 80% of the roof of the building on the efficient building, and then that would cover all of the energy use on an annual basis. So we could really get it down to zero. And the efficient envelope includes better insulation, better windows, tighter building envelope, which is weatherization, sort of those two are similar. So all those best practices, but nothing crazy. But it's insulation is not high tech, but we're just using more of it, But using the best windows with the low E coating and different things like that. Yeah.
Does everyone have to follow the ASHRAE, American Society of Heating, Refrigerating, and Air Conditioning Engineers standard?
So the ASHRAE standard has been adopted in some states as a energy code, but in many states it's not required. And then several countries around the world use a ASHRAE standard directly or as the foundation of their own national building energy standards. So in the US, I don't know the exact numbers, but I think it would be about half the states have a required energy code for buildings. But that probably, those half states, one of them is California, probably represent 3/4 of the US population as far as people, right? So if you think about high population states like California, Florida, New York, Texas, Washington State, all those states do have energy standards for buildings. Some are more strict than others, right? So what are the next generation of energy efficiency blockbusters? Heat pumps are a front and center thing, and I'm going to talk about that a little bit more in detail. This idea of integrative design, there's a whole class on integrative design here taught by Emery Lovins. And if you have the ability to take that class, I would recommend it. And the idea of integrative design is how do we integrate these ideas together to come up with a more creative solutions. So if you think about it like a battery electric car, okay, it's not that engineers took a normal car and put batteries into it. What they did was they said, well, can we actually design a more slippery car? A car has lower resistance. Can we do that so that the batteries are smaller? And then because we don't have the need for a huge trunk in the front, maybe we can have the front be a little bit come down a little bit to make it more aerodynamic. So there's all these interactive effects. So that's integrative design. So if I put better windows in building envelope, can I make the heating cooling system smaller, right? So you start working together. I'm simplifying what can become a very complex set of interactions. But that's the integrative design. Induction cooking, which I'll talk a little bit, is another big blockbuster. And then solar and batteries. And solar and batteries can and is being used, are being used at the building level. They're also being used at the grid level. And you guys have learned about that, but that's a big deal. And then in the middle there, AI for energy optimization. In fact, I wrote a paper with a few graduate students here about how AI is going to change how we design buildings, but also how we operate buildings. And deep optimization is going to be possible. We think that in existing buildings, the possibility of lowering energy consumption by 5 to 10% is a realistic estimate of where we're going to be with AI in not too distant future. So I think that's going to be very big. All right, so when we look at it, what we're saying is on the left, we could have not very much building efficiency in the center there, but then that means we're going to need a bigger on-site generation or renewable energy or smart grid or energy storage. These things are going to have to be bigger. Or we could take the path on the right, which is if you make the building efficient as a key strategy, then we're going to need less on-site generation or less renewable energy, less grid, all these things. So oftentimes people think about the supply side. We're just going to build more and more solar. But if I said to you, well, if we make buildings efficient, we can build 30% or 50% less solar and 50% less power lines and battery storage and all these things that are difficult, but good, right? The right thing to do. The efficiency is going to win. And then the other thing that a lot of people talk about is like how fast can we decarbonize? Speed matters right now from a climate change perspective. So we need to move quickly. And to say, well, efficiency doesn't matter, we'll just get photovoltaics and wind power to the building. Well, okay, fine, that's happening, but it's just going to take longer for us to decarbonize fully or to have dramatic reductions in carbon emissions. So that's a important thing. There's a retired professor, Jim Sweeney, here from Stanford, that with some graduate students wrote a book on energy efficiency's impact at a macro level. So the whole economy, and they focused on the U.S. economy, and saying, okay, if we had the same efficiency equipment that we had in the 1970s and it just got locked in at that efficiency, so car efficiency, building efficiency, all trucks, like aviation, if all those things were locked in at the efficiency at the 70s, we would have an energy consumption that's significantly higher than where we ended up. And their study was through 2015, so it's a little dated now, but the data is important because it's a decades-long study. And what they found is that energy efficiency reduced our demand by 30% in the US, which is more significant, like almost by an order of magnitude, than all the solar and wind and nuclear, all those things that were added to the grid during that same time. So energy efficiency is not something that we hear about a lot from, politicians or policymakers, but it is a workhorse of meeting our energy services demands. right? We don't really have energy demands. We have a demand for energy service, right? The saying goes, we want hot shower and cold beer, right? We don't necessarily want kilowatt hours or BTUs. Those things don't necessarily matter to us as individuals, right? So we do need to focus on what is it that we're trying to achieve here. So, okay. All right. So that's energy efficiency. The next thing that we need to focus on is how do we electrify buildings? Remember, if we're building or if we're burning a fossil fuel at a building, like for heating, that's just we're just burning fossil fuel and emitting CO2 at the building. And we think, oh no, it's just a little thing. Like the boiler for this building would not be very big, just be like a third of this room. But that thing is putting out CO2 every single day. And remember what I said, when you add it all up, 2.4 gigatons of emissions for heating buildings, primarily space heating, but also water heating. So it adds up. So we want to electrify buildings. We don't want to be burning fossil fuels at buildings. If we look at, and this is US data, residential buildings, half of their 52% of their energy requirements, all energy requirements like lighting, everything put together, is met with fossil fuels. And then in commercial buildings, 34%. Okay, so that's mostly all about heating again, heating or water heating. So it is a significant part of the overall energy picture. Okay. But if we look at it, 24 in the US, and again, we could look at this globally. 24 states have committed to have zero carbon electricity by 2050 or sooner. There's already a lot of countries that have zero carbon electricity: Costa Rica, Kenya, Uruguay. The list goes on of countries that are in 90% or higher of their electricity is carbon free. It's surprising to me because I looked at it recently, and then the number's somewhere in the neighborhood of 20 or a little bit more than that. So, California, for example, is moving quickly. We're already at 60% carbon-free electricity on a annual basis, and by 2045, it's legislated it has to be 100%. So, how do we electrify buildings? For space heating, we can use a heat pump. I'll talk about that in a second, describe it. For domestic hot water, we can use also a heat pump. We can use electric resistance heating, but electric resistance heating, which has been around for a long time, is very energy intensive. For gas cooking, we can go to electric resistance cooking, or the better, more modern version is called induction cooking. So if we look at heat pumps, how do those guys work? With a boiler, we put in 100 units of heat and we get out 85 units. We put in 100 units of fuel and we get out 85 units of heat. That's an 85% efficient boiler. That's how we do fossil fuels. And it could be a furnace, it could be a boiler, whatever. For heat pumps, you put in 100 units of electricity and you'll get 300 units of heat out. You're like, wait a minute, that doesn't sound right. The way heat pumps work is they are able to pull heat out of the surrounding, usually air or atmosphere, sometimes connected to the ground, and it's able to move that heat into the building. It's the same way a refrigerator works. Refrigerators pull the heat out of the cold box of the refrigerator and dump it into the kitchen. That's how refrigerators work. It's the refrigeration cycle. So we can use that same refrigeration cycle to pull heat out of a cold environment outdoors and put it into the building. So we triple the efficiency. So heat pumps are a big deal on efficiency, but they're also a way to electrify heating. So they, in a sense, we're killing two birds with one stone, right? Or you can have your cake and eat it too, or whatever, however you want to say it. So if we look at it from a carbon perspective, if we have a boiler putting out 100 units of CO2, it could be 100 kilograms or whatever, that same heat pump, if it's powered by natural gas at a power plant and creating electricity, because the power plant's efficient and heat pumps are super efficient, we'll get 54 units of CO2 out or emitted at the power plant if we use a electric heat pump at home. So even, and this is the thing that they say about electric cars. So wait a minute, if that electric car is charged with electricity made from CO2, is it really actually improvement? Yes, it is, because the electric motor in a car is so efficient in the 90% range as compared to internal combustion 24%, right? Electric cars are so much more efficient, even if they're charged with natural gas power plant, you're still having a big reduction in carbon emissions. Same thing with heat pumps. Even if we have a 100% natural gas grid, we're cutting our CO2 emissions in half. But most grids in the US and globally are not 100% gas or 100% coal. There's some mixture. So if you have a situation where ultimately we're able to plug that heat pump into a zero carbon emission grid, we can get the CO2 emissions down to zero. I have solar on my house, and I also try to run my heat pump when it's the daytime, when I know there's more solar electricity on the California grid. So I'm trying, between my solar on my house and getting solar from the grid, or renewable electricity from the grid, I'm close to running my heat pump with zero CO2 emissions. So something to think about. Now, heat pumps, remember back to that number, 2.4 gigatons. Heat pumps have the potential to take this and eliminate that thing. Heat pumps, when you talk to people at these energy agencies, like the International Energy Agency that's based in Europe, it's globally thinking about energy policy globally, heat pumps are like a huge part of the conversation. Okay, so I don't mean to harp on like just a heating system, blah, blah, whatever, right? I don't care about how I get heat. I just want heat. Don't tell me about like, but heat pumps are really big. They're a really big deal. So anyway, this is what they look like on people's homes. We actually have had heat pumps. You can get an air conditioning unit that can reverse and do heating as a heat pump. On the left, we had those kind of things for several decades in the US. But more commonly are these skinnier suitcase-shaped units that are very popular in Asia, and those are now globally available. I have one of those on my house here in California, and it can do heating or cooling. One piece of equipment can do either because it uses that refrigeration cycle. So it's actually really nice, right? So, but in commercial buildings, there's bigger versions. They come in a lot of different shapes and sizes. The left one is what's called a variable refrigerant flow system, does heating and cooling. On the right, those are big boxes that make hot water for domestic hot water. That's on a apartment building project that I worked on. So, yeah. And then you can really scale it up. Stanford has a central energy facility that makes heating with heat pumps. It uses these big machines called chillers. They make chilled water for cooling buildings as well as hot water. It makes both, and it stores them in those big tanks there and then distributes them around the campus. So it can be really small, and it can scale up to really big. So a little bit about gas cooking. Gas cooking is popular in a lot of places. Electric resistance heating is also very popular, but gas cooking. The problem with gas cooking is it does emit a variety of pollutants into the kitchen area: nitrous oxides, carbon monoxide, formaldehyde, and now a group at Stanford has been doing a lot of research on benzene emissions from natural gas burning in the kitchen. And benzene is a very well-known carcinogen, not to be ignored, and the levels are well above what's considered to be safe in kitchens. If you do have a gas stove, you should always use the exhaust when you're cooking. But induction cooking is the modern replacement to that. Gas cooking, because so much of the heat goes around the pot, it's only about 30% efficient. Induction cooking, we can get up to 80% plus efficient. So significantly more efficient, but induction cooking uses a magnetic field to heat the pot. It moves really fast. It typically boils water faster than gas stoves. It's more precise. You can get to the temperature you want more quickly, so medium high, and it's not like the electric resistance stove of the past where it's really slow and it has that coil that heats up. It doesn't do that. It's a magnetic field, right? So there's commercial versions of it, there's residential versions of it. So anyway, if you think there's all these strategies for electrifying buildings, now there's all electric or zero emissions building codes in a variety of places in the US. And generally, what we're seeing is the market for these things growing very rapidly. In 2023, heat pumps in the US, there were more heat pumps sold than there were gas furnaces crossed over. Europe is going very hard into heat pumps. Why? Because they discovered that their natural gas supply from Russia was somewhat fragile. And so there's a big push to transition there. And a variety of other countries in Asia are also focused on that. I have a couple students in my class who are from the Middle East, and they're like, hey, Peter, energy in our country is super cheap, really, and it's like water is cheaper. Water is more expensive than gasoline and things like that. But what they've told me is that water heating in these countries is Saudi and Kuwait. Water heating, the vast majority of water heating is done with heat pumps. Interesting. So we're seeing a lot of movement in that electrification. And then building renewable energy is the last little piece of our puzzle. And the thing you should know is that when I was your age, solar costs about $20 per watt. Today, it costs for a solar panel, just the PV, it's down around 20 cents a watt. That's a factor of 100 reduction, not a factor of 10, 100, $20 down to 20 cents. So solar is, every time it goes down, there's a surge in use globally. Globally, last year, 80% of all new electricity added to the grid was either solar or wind. 80%. Okay, so solar and wind have become not just sort of affordable, they've become more affordable than gas and coal and nuclear power plants, right? And that's why there's just a surge in growth in solar. But at buildings, we can put solar on the roof, we can put solar over the parking, there's a variety of things. Now, if you're in an area like my students who are in the Middle East, where you're like, electricity is so cheap, they're like, okay, we're not going to put solar on our building because electricity is so cheap. But most people in the world live in places where electricity is relatively expensive. And putting solar on the building, even if there's solar on the grid, solar on the building can be an affordable way to generate your own electricity. And so we are seeing a continued interest in solar on buildings. In the U.S., there's a variety of states that have this net metering. If you generate one extra in the kilowatt hour of electricity in the middle of the day, you can send it back to the grid, and the utility gives you full credit for that, and then you can buy it back, or you get credit for it, you get it back at night, in essence, for free. So it's called net metering. Now, in California and some other places, they're starting to say, wait a minute, you need to pay extra for grid services. But in many countries, 80 countries, in fact, there's a feed-in tariff idea where they're not just giving you credit, they'll pay you extra to send solar-based electricity into the grid. So there's a variety of ways of incentivizing generating electricity at the building. And then the other thing that's also coming down now is batteries. You guys have probably talked about that. Battery costs, they're not done coming down. I'd say solar, we're sort of near the bottom, 20 cents. But batteries are still coming down, but they've come down dramatically in the last 10 years. And so that's making the use of batteries at the building very interesting and attractive. So we're starting to see battery storage at buildings for a variety of reasons. right? Resilience, like a power outage, but also if I have extra solar that I'm sending back to the grid, and like in California right now, they're like, well, we don't really want, we have a lot of solar, we don't want it so much. Well, you can keep it at the building with batteries. And then the other thing is now electric rates are starting to have different time of day rates. And so what we can do is when during different, if the time of day is cheaper electricity, you charge up the battery. And then when electricity is really expensive, you stop buying electricity from the utility and you just use the battery to power your grid or your building. So we're starting to see a lot of batteries. And then, solar batteries at the building, but we can also now buy renewable electricity from the grid. And there's a variety of different programs. What I found out is that globally, many different countries have programs in Europe, Asia, US, where you can, if you don't have solar at your building, but you want renewable electricity, wind or solar, you can ask for that. And in the US, we have this thing called community choice aggregation. It's one of the more popular ways of doing it, that I can say, I want to buy, and if there's a little extra charge, I'm okay with it. Usually it's like 1% to 5% extra, very small amount of additional fee to know that 100% of your bill that goes for generation is going to a company that's generating using wind or solar, right? You don't actually know that the electron that gets to your house is from that. It doesn't really matter, but it's just that your generation part of your bill is going to a renewable provider. Okay, so that's happening. So, all right, so you actually put it together, efficiency, all electric, and then renewable. That the operational decarbonization is actually quite straightforward. And so I'm just going to share a couple of case studies where we've done this. This is a building that we did in Alameda, California, which is just 20 miles from here. And it was a developer built building. The developers are like, we want it affordable. Don't spend your extra money on that green thing. You know, they're really like, Peter, they're like, we love that stuff, but we're not paying extra for it. So we said, okay, we're going to do a building that's first efficient. And you can see they're shading, modest, but shading on the windows and good glass, and not a massive quantity of glass, although the lobby is very glassy, but the rest is more modest. And then efficient lighting. And then we did all the efficiency things. We got 35% lower energy use before the solar, and it was fully decarbonized. So we use heat pumps for the heating and cooling system. We did the variable refrigerant flow system that does both. One unit can do heating or cooling, depending on the season, right? So that we did that. It's all electric there. We did 100% electric kitchen. This is a photograph of the actual kitchen. So there's no natural gas used in that kitchen. It's like it's a high-end corporate kitchen with fryers and a cooktop and ovens and the whole thing. And then they put solar PV on the roof and in the parking lot. 50% is on site, meaning at the building, but then the other 50% electricity that they need, they buy from the utility. So happens that it's a municipal utility in Alameda, and that utility is already, as of 3 years ago, buying 100% of their electricity from renewable sources, geothermal, wind, and solar. So they are 100% electric utility. It's somewhat unusual. So this company, even if they didn't have solar, they would have had 100% renewable electricity, but they wanted the solar because they did the economics of it and said, okay, this is saving us money and giving us a good return on our investment. So that building is fully decarbonized from an operations perspective. Really love it. We're doing, I've worked on this American Institute of Architects headquarters building in Washington, D.C. It's a few blocks from the White House. And first, we're making it more efficient. This is a renovation of a 1970s era building. So we're going to make it efficient with LED lighting. We're putting in new glass. We're doing a lot of nice things. We're taking the old natural gas boilers, replacing them with heat pumps on the roof. And then how are they going to do the renewable energy? They have a little bit of solar on the roof, but it's a 7-story building and the heat pumps are up there. So they're going to buy renewable energy from the grid. And Washington, D.C. does have a program called Community or DC Power Connect. And they're going to this clean choice energy company. It's one of the options. And they're going to be buying 100% solar and wind. So that operational decarbonized. The cool thing about this project is about the embodied carbon. First thing, if you think about it, building a new building versus renovating an existing building, if most of the embodied carbon is in the structure, renovating an existing building is better. And they did actually look at buying or building a new building on more in a suburban area. And they said, no, let's stick with the existing building, lower embodied carbon, and a little bit cheaper as well. And then they did a lot of renovation, lots, new glass, new furniture, that has embodied carbon. So what they're doing is they bought solar panels and donated them to Habitat for Humanity. And then Habitat is installing them on low-income homes in Washington, D.C. and Northern Virginia. And what happens when those panels go on the building, it offsets electricity that is generally the mix does have a high percentage of natural gas power plants in that area. So those power plants are going to use a little bit less energy, a little bit less CO2 emissions. When you add up for the number of solar panels, it equals the embodied carbon of the building. And the number of solar panels, we calculated how many solar panels they would need to donate to equal the embodied carbon of the new things going into the building, the glass and furniture and stuff like that. Interesting. So this building will be operationally decarbonized and embodied carbon decarbonized. I believe it's going to be the first building in America that will be fully decarbonized. So that's very, very cool. So I've also been working in India for about 15 years with a company called Infosys. If any of you are watching the French Open, which I've been watching lately, it's really cool. Infosys's logo is down there on the things. They're a big IT company in India, and they work with Fortune 500 companies from all over the globe. They have 300,000 employees. I have to check every time. Last time I had this slide, it was 250. They've grown a ton. And then they have 40 million square feet of offices. And they've gone and on a program where we work together and reduced their energy consumption by 55% during that time. And that's per employee. But they went in hard on the energy efficiency and found that they were able to save a lot of energy. So they do all the right things. They have better glass and better building envelope. They have a very low friction system for the distributing the heating and cooling. They end up with spaces that have good daylight, are physically more comfortable for their employees, and at the same time use less energy. And what is so amazing is they've sort of cracked the nut on how to make that affordable. So their buildings, they don't spend any more money on their buildings than what would be required in the Indian office building market. So it's an amazing case study. They have a whole book that they've written about it that's free online if you're interested in more of the details. So with that, I'm going to end. I do teach this class spring quarter called CEE 226E, techniques and methods for decarbonized building design. So students get into like, how do we apply these straightforward techniques to design a decarbonized building? So the students design a decarbonized building. It's a group project type of class with a variety of assignments as well that get you experience on how that's all set up. And then also we have set up the Stanford Building Decarbonization Learning Accelerator, where we've created a wide variety of teaching material on building decarbonization that we make available to professors and lecturers around the world. And we now have over 200 universities that are using this material, and a variety of professors, and then also private companies that are using this material, trying to get either students, most importantly, but also clients and larger companies thinking about this decarbonization because it is straightforward but it's a different way of doing buildings. Remember that what I started with, that there's so much momentum in the way we design buildings. It's hard to get people to sort of change, even if the new way of doing it is actually very affordable and simple and straightforward. So thank you.